So welcome to the lecture on timers in STM32F100RB microcontroller. Before we start discussing anything about the timers on this microcontroller, we'll quickly brush through the basics of timers. So basically timers are counters that count a clock pulse. These might be up counters, down counters, or configurable for both up and down counts. They are usually used for timing operation to a level of precision which is much superior to having a for loop run and waiting for the program to fall through a for loop. In general, they are 8-bit, 16-bit, or 32-bit timers in the industry, and many timers are used to run other modules like clocking for the UART or the DAC on the chip. Examples of using timers is, say, if an RTOS is running, then a timer is always used to run the system clock for the RTOS. Or for example, if there is an assembly line and there are two stations on it, and you want to time an job to move from one station to the other, precise timers are used for this operation. Or for example, the coffee vending machines might have timers to dispense out an exact amount of liquid at a given flow rate. Finally, uses like measurements between events, clicks, or waiting for some time are other important uses of timer. For example, if someone has to wait between a button click and then perform an operation, timers are the natural choices. So with this, we'll continue to learn something more about timers on the given microcontroller.
So now that we have learned something about timers and their uses in embedded systems, it is time that we deal with something known as the basic timers of STM32F100RB. The timer number 6 and 7 in this microcontroller are called the basic timers because they provide very basic functionality required for timing operations, and more complex operations are not provided, or more complex features are not provided with this timers. So to understand the basic features of this timer, both of them are 16-bit timers, up counters basically, and they have programmable prescalers which can prescale their clock. That is, the clock which they count can be reduced by a factor of anything between 1 to 65535. That is, anything that can be expressed in a 16-bit format. Also, they provide a synchronization circuitry to the DAC. So whenever the digital to analog converter unit needs a trigger event, these timer events can be used. The timer number 6 and 7 can be used as event to trigger a DAC conversion. Also, they can have an interrupt or a direct memory access generation event on counter overflow. With this, we come directly to the resistors and the code simultaneously. Let's take a look at the code. To start off with, I have a flag that I've declared, which I'll be using later on in the logic to turn on and off an LED. The task for this code will be to blink an LED with a precise timing of 1 second, with 1 second on time and 1 second off time. This exact precise accurate timing is achieved by using the timer number 6. So this flag has been declared as an unsigned character. After this, we use the normal system init function. In this function, we are making sure that the CPU is clocked at 24 megahertz. This is very essential in timer programming because we should know what clock is driving your entire peripheral bus, so that the timer is clocked with a particular value, and then the prescaler that we enter will divide this clock, and we will be in a position to judge what is the delay or what is the time duration that we have programmed into the timer. So after this, we come to the initialization of the RCC resistors. Both these are enabling the clock, one to the timer number 6 itself. So the entire module, the peripheral, gets its clock, and the other is to the GPIO C, so that we can blink the LED which is connected to GPIO C. Just to make sure that we are doing everything right, we'll go to the RCC registers, and in that we'll come to the clock enable registers, peripheral clock enable registers. Yeah. So you have to find out where is the timer 6 bit. This is in APB2ENR. We have the GPIO C, which we have enabled here. You could just see in 2 we have enabled the GPIO C, and in 1 the 4th bit needs to be for the timer. We'll just check this. Come down to the APB1ENR, and the 4th bit is for timer number 6. So we are pretty much sure that our timer 6 and GPIO C modules are now clocked. We'll come back to the timer registers. Next, this is a very common line by now. We are making sure that the GPIO pin, GPIO C, and that to pin number 8 on this GPIO is configured as an output push-pull mode for a 2 MHz operation. Now, next line loads a register called the auto reload register with some hexadecimal value. For this, we will refer to this Word document. It says that the required delay that we want to produce is of 1 second. Next line tells us that the clock is a 24 MHz clock. Now what we have to do is we select an arbitrary prescaler by which we can do a trial and error method, of course, but just because from experience I know that a prescaler of 1000 will do the job, so I've selected a prescaler of 1000. Now this means that the 24 MHz clock will be divided by 1000. So 24 into 10 raised to 6 divided by 10 raised to 3 will be 24 into 10 raised to 3. So the clock received by the actual timer register, which increments on every clock cycle, is now 24 kilohertz. Now we will find out in time domain how much does one tick of this timer last for. So that will be 1 upon 24 into 10 raised to 3. So that comes somewhere around 41.66 microseconds. 41.66 microseconds. Now this time is for one clock tick. Now we want to find out how many number of clock ticks will make up a delay of 1 second. So we divide 1 second by unit time of clock, that is 1 divided by 41.66 microseconds, which comes out to be 24004 in decimal value. If we just enter this into a programmer's calculator, see, selected as decimal 24004 and convert it to hexadecimal, we get this value of 5DC4. That's what we have entered here. So now this auto reload register has been loaded by 5DC4. So now let's check out why are we doing this. We'll come down to this register a little later, though it has been given before in the data sheet. For proper working of the code, it is necessary that you load these registers before. Let's just pass through. That's the status register. Yeah, the auto reload register. Now it says that the auto reload register is the value to be loaded into the auto reload. ARR is the acronym for the auto reload register. Now what happens is the counter is blocked while the auto reload value is null, so that when this is null, the timer will not work. As soon as you load this value with a particular value, load this register with a particular value and enable the counter will count up to this particular value. Whenever it equals this value, the value in timer register ARR, and status register of overflow will be detected as soon as the register overflows, that is ARR plus 1. This tells the programmer that the required time duration has elapsed, and that is why we are loading the required time duration into ARR. Next, the statement over here loads the value for a prescaler. Now we have decided that the prescaler value should have been 1000. Still I am loading a value of 999 decimal here. This is because, come to the description of the prescaler. The counter clock frequency CKCNT, which is 24 kilohertz now for us. That is the actual clock frequency divided by our actual clock frequency is 24 kilohertz now, and we have to program CKCNT. Is prescaler is the clock frequency to the microcontroller divided by a prescaler plus 1. So if the entire prescaler is kept as 0, still the entire frequency will be divided by 1. So if you want prescaler to be 1000, we have to program the value of prescaler as 999. So that's why in this instruction we are loading the timer 6 prescaler by 999. Next, now we come to the control register 1. This, though it is given first in the data sheet, in the reference manual, it is necessary that few registers are preloaded so that the operation of the code is not hampered. Just a good programming practice. You can still go in line with the reference manual and get the required results most of the times. We'll come to the first register of timer called the timer X control register. Now let's see what the code says. It says that the 7th bit is set to 1. This means that the ARR register is buffered. Now this buffer is a digital buffer. It stores the value to be loaded in the actual ARR register in a buffer. This means that whenever the timer is running, and if time X ARR register is buffered, that is this bit is set to 1, then till the time an update event is not generated, the new value will not reflect into the code. Now there are two ways of generating the update event. One is by having an software based update event, or by having an update event at the time of an overflow. So for now I want my register to be buffered so that when the timer is running in one cycle it cannot be disturbed, that is the ARR register cannot be disturbed. Next, it says that the third bit is set. The third bit's implementation is 1 pulse mode. In 1 pulse mode, whenever this is set, the timer is put into a 1 pulse mode. That means the counter stops counting at the next update event. Now and it will clear the counter enable bit. This means that the counter stops the minute it has an update event. Now this update event can be via a software update, which is in the middle of its counting, or it can be on an overflow. When you need the counter to be running even when you are processing the overflow event, then you have to keep this bit as 0. We will be using 1 pulse mode, so we have set the bit. Next in line we are setting the second bit, and it says and update only on overflow. So let's see what the implementation means. Setting the second bit, it means the update request source. From where will this counter update its ARR, the prescaler and other registers? When set to 0, any of the following events generates an update event or a DMA request if enabled. The events are counter overflow. There can't be an underflow in this as it's an up counter. Setting the UG bit, we'll come to this bit a little later. Or update generation through the slave mode controller. Now slave mode controller will come into action when we learn the other advanced timers. These timers have a possibility to use timer number 6 and 7 as their slave timers, so that they can start their counting. The advanced counters can start the basic counters and stop them as well, or give them commands to update. For now we don't want any of these two facilities, so we are using this bit with one value programmed in it, which means that only counter overflow generates an update interrupt or a DMA request if enabled. DMA again we are not using, we'll be using an counter overflow. The next bit in this register make sure that the updates are disabled, so that if this is set to 1, then the update event is not generated. Shadow registers keep their value, that is the registers from which the buffered registers from where the timer and counter is actually working. However, the counter and the prescalers are reinitialized if the UG bit is set or if a hardware reset is received from the slave mode controller. These are advanced features, we will not be using this. So anytime when you don't want an update event to affect your registers, then set this bit to 1. We will be keeping it 0. The next bit is the counter enable. Should the counter start counting the clock that it is receiving, or it should stop? If it is 0, then the counter is disabled. If it is set to 1, then the timer counter register will start counting the clock pulses that it receives. Next note, I'll just go through this note. Gated mode can work only if the CEN, that is the counter enable bit, has been previously set by software. However, trigger mode can set the CEN bit automatically by hardware. This kind of modes we are not going to use currently for any of the tutorial based codes, and if you need any help, it is freely available on the net. Another note over here is, in one pulse mode, the CEN bit is automatically cleared by the hardware. So whenever we want to restart the counting, we have to set this bit to 1. That's what we'll be doing in our code. The control register 2 is the register reserved for the master slave kind of operation, and we'll cover this when we cover a advanced timer. Next register is the timer DMA or interrupt enable registers. This we will cover while interrupts are being covered or DMA is being covered. For now, we will not be touching this register at all. This register is called the status register. Now, status register will give an value of 1 in its 0th bit if there is an overflow, or when the counter is reinitialized by software using the UG bit in the timer event generation register, and provided if URS, that is update request source, is equal to 0 and UDIS is 0 in the timer 1 register. We just go back to these bits. That is, the disabled is 0, that is the entire thing is enabled, the update requests are enabled, and the sources are common source. If this is the condition, then you will find that the status bit will be 1 when the counter is reinitialized by software using the UG bit in this register. This is the event generation register. We are not going to use this value, however, we'll just go through this. This bit can be set by software, it is automatically cleared by the hardware. What it does is, when set to 1, it reinitializes the counter and generates an update of the registers. So basically it's used for updating the shadow registers with the new values of prescaler and the ARR register. Note that the prescaler counter is cleared too, but the prescaler ratio is not affected. This is because the prescaler counter is cleared only after its value is copied to the buffer registers. This is the actual counter. What it says is, it's a read-write register. It means that this counter can be dynamically written into and also dynamically read out, so that if in a particular application, if you want to curtail or enhance that is elongate the timing that was pre-programmed, you can always read and write into this register. Because one point to notice, this is very important, you cannot tamper with ARR unless you generate a update event. So to change the timing at runtime while the counter is running, you have to write or read and write to the counter register directly. Prescaler and auto reload registers we have already studied. With this we come to an end of the registers. Now we will come back to the code. these three lines we have already seen. Next, I am making sure that this logic is set, the flag by which the entire logic works is at 0 to start off with. And next, we have already seen that the 0th bit in CR1 was the timer enable. So I enable this timer. Next, what I do is I reset the status bit as, for any reason, if this has been set to 1, its value is now 0. And now we come to the main logic of while 1. In the while 1 loop, what we do is the very first line, we wait till the time the status register's 0th bit, that is the actual status of overflow, is becoming 1. So what we poll for is till the time this bit is 0, stay in this while loop, and this while loop has a semicolon. So the program will not fall through till the time the status bit is not equal to 0. Next, if the flag is if the timer runs out, we will fall through and we'll execute the if else statement. In the if else statement, if the flag is 0, then I set the 8th bit on the GPIO C port so that the LED glows, and next I make the flag 1 so that next time when I come to this loop, my else part will be executed and the and equals not macro will reset the LED bit so that the LED will become will switch off, and again the flag is set to 0 so that again I execute the if loop. Next, what I do is, remember I'm using the timer in the 1 pulse mode, and in 1 pulse mode the enable counter enable bit becomes 0 after an overflow has occurred. That is why I restart the timer by setting the enable pin, and the status register is also cleared. Else what will happen is, as soon as you execute this code, you'll come back here and this time this while loop will not work and it will not wait till the time the counter has counted 1 second. It will directly fall through because it won't be 0 here. That is why I reset this bit here and again wait in this while loop till the time 1 second passes by. This is how this code works. What we'll do is we'll now connect the kit and try and load this code and see how the LED blinks with 1 second on time and 1 second off time.